And then
Hi, this is recap lecture number 3, and I'm actually going to start out with having you pause the recording almost right off the bat. You'll see that the first page of the notes is to write down a whole bunch of rules about derivatives and integrals. And I just want you to quiz yourself by writing down all that you can and then start the recording again. Okay, so hopefully you just tried that on your own. And this is my page of answers, so we'll just take a minute to have you look and make sure that you are in good shape. Okay, so notice there was a kind of mean question on my part, which was the natural log of x dx. That is something that we do not yet know. It is not on the list of topics for the AP test. It requires something called integration by parts, which I intend to have us study after the AP test, since it's not an AP topic, but it is commonly in a first-year course of calculus at colleges. Just make sure that your answers are all lining up. Pause the video if you need to look longer. And the next slide is similar to something that we did when we were working in Chapter 5. I think these are really great problems. They are integration problems where you need to decide what family or what category each one of them is a part of. So let's kind of work these together. First guy, I hope you recognize it to understand is our sign of x straight up. And the next one looks really similar to that, but the fact that it has an x in the numerator actually makes it quite different. How would you do this one? You said it's a u substitution. You are correct. You would let u equal the part inside the square root in the denominator. Du would be negative x, 2x, dx, which means you would need to insert the negative 2 and the negative 1/2 on the outside to make everything line up. It's not turn into natural log. It is merely a power rule situation. I just wanted to point that out because I did grade some papers recently where that was a common issue. Just because something's in the denominator, if it has an exponent, it's just going to be a power rule situation, not a natural log. The next one looks a little bit like arcsecant, but the parts inside the square root are reversed, so that is one that we do not yet know how to do with what we know thus far. All right, in the next line, the first one, what do you think of that? That is one that we do not yet know how to do either. However, the one next to it is very similar, but enough different to allow us to do the integral. We would do a u substitution here, where u is equal to x squared, which means that u would equal 2x dx. And so again, you'd insert a 2, balance it with a 1/2, and you have something in the form of the integral of e to the u du. That is also the case for the next one. You would let u equal x to the negative 1, and that means the derivative of that would be negative x to the negative 2. And so all you need is to insert some negative signs. That little speck there's supposed to be made with a negative sign. Just insert two negatives, one on the inside, one on the outside of the integral, and you should be good to go on that one. In the next line, what do you think of the first guy? Okay, we can't do that one yet. Okay, however, we can deal with the next one. If u is equal to this denominator, actually take that back. That's not what we want to do on that one. That's what we want to do on the next one. Let's talk about that one then. So on the next one, we want u to equal the denominator because du is equal to 4x to the third dx then. And so again, that's just an inserting of some constants, and we're good to go on that. The previous one, in this one, this is kind of tricky. You want u in this case to equal x squared, because then u would equal 2x dx, and that works well with what is provided on the top. And then if you do all the substitution, you'll see that you actually have something related to arctangent. So that has kind of two layers to it, a u substitution layer, and then after the substitution, you end up with arctangent. All right, the next couple problems that I have for you go to the world of derivatives rather than integrals. And they were both the kinds of questions that you might have seen in Chapter 5 in your book, as were the ones we were just talking about with the integrals. So in the next problem, you could just hammer away with this with calculus, but it would be so much better if you used log properties first and separated this out into pieces. That's supposed to say natural log. And then subtract. Use your log properties, and then all these little bits are easier to take derivatives of rather than one big chunky thing that's going to use product and quotient rule. Ick. So now we have a derivative, and we use just 1 over u du as our rule, which is just much, much, much easier, especially when all the derivatives of these things are ones anyway. This is so much easier. That would be it, okay? The log properties can definitely help us out. On the next one, this is going to involve some chain rule. And so to take the derivative, we'll think of the square root as a power. So we have 1/2, keep the inside, knock down the exponent to a negative 1/2, and then chain rule, we have to take the derivative of the inside. And the derivative of e to the u is e to the u du. So we'd have 2 e to the 2x minus 2 e to the negative 2x from chain rule. And that would be it as far as I'm concerned. If you had more that you needed to do, then you might want to have it in a slightly neater form. Okay? The next one is to review implicit differentiation a little bit, which was the topic of an earlier video, a topic in an earlier video. But this problem involved E, and that was, again, something that we couldn't have done at the time that we did implicit differentiation because we didn't have anything about E at that point. Understand that the left-hand side of this equation is not cosine of x times cosine of x. The intent of what I wrote is cosine of x times x. Okay, so it's x squared inside the cosine function. Our derivative of cosine is negative sine. We keep the inside, take the derivative of the inside by chain rule. On the other side of the equation, we need to use product rule. That would be first derivative. Oh, sorry. Writing with my finger is not the best. Okay, so first derivative of the second plus second derivative of the first, and that would just be a 1. Oh my gosh, it looks like a kindergartner wrote it. Scary, scary. Okay, so now if we wanted to isolate the dy dx, okay, now that looks a little better. I think I got a better corner of my finger. Okay, so for dy dx, we would have all the things that are currently on the left-hand side, and I'm going to subtract that e to the y over to this side. So sine, must be hitting something. Sine, let me just try to undo that real quick. Sorry about that. So sine, hold on. Okay, I just paused the darn thing. Well, I struggled through writing that. I'm not sure what's happening. This is what you would get just isolating the dy over dx. Okay. The next question asks you to find the area bounded by these different curves. So why don't you go ahead and pause and try this problem, because I don't think there's anything super tricky about it. But try this problem yourself and then come back and we'll check. Okay, so hopefully this is what you set up. You're trying to find the area of the region I colored in yellow. That means you're going to integrate top minus bottom. The bottom here is just 0, so you could just write the integral as the top function. And you'll see that I balanced the integral out by inserting some constants that I wrote in red pen there. My antiderivative, therefore, would carry along the negative 1/2 and then just be e to the u. And I have my 2 bounds there. And then when I substitute those bounds in, we should get negative 1/2, let's see, e to the negative 16. And then when you plug in the 0, you just have a half because e to the 0 is 1. All right, the next thing that we're going to review today is our famous buddy points theorem. I don't know if this is picture. Clearly, I stole it from the internet because I think I'm not great at drawing it. The idea is that if you have 2 functions that are inverses of each other, the slope of these corresponding tangent lines are going to be reciprocal. They have reciprocal slopes at these corresponding points that we call buddy points. And the thing that is tricky is that the x coordinate on one of the functions becomes the y coordinate on the other and vice versa. you need to pay attention to which thing you're plugging in. You need to make sure you're inserting an x of the function that you're referencing. So here's a problem that we can do together, and it's sort of a complicated one in that the function itself is kind of disgusting looking, the piecewise function. For this, you'll want your calculator, so if you don't have that handy, just pause and come back with your calculator. But the question itself asks us to find the derivative of the inverse to f, derivative of the inverse to f at 5. So I read this as understanding I want f inverses derivative at 5. And I want to make sure that I understand that what this implies, among other things, is that f inverse has an ordered pair of 5 comma something, which means function f, as f inverses inverse, has a 5 as a y coordinate. So this is where you need your calculator, because if you just set each one of these equal to 5, it's not real clear like how to algebraically solve that. So what I did is I just went on my calculator and I graphed these two piecewise functions. So the first function, even though it looks weird, is actually just a line, y, and then this is the m, x, and then this is the b. So if you graph that, you get this nice little linear function, but it stops at 2. And then after that, this function picks up and it actually continues this line. I know my line doesn't look very straight, but just go with me. And it has this little like kind of steppy step look to it, but wavy because it uses the sine curve. And then if you also graph y equals 5, you'll see that it's the second branch, the second piece of the piecewise function that hits at 5. You set that equation equal to 5. It isn't really clear like what the actual solution is, but once you find out what the solution is, it does make sense. So this point of intersection corresponds to an x coordinate of 4 and a y coordinate of 5. So that tells me the other half of the buddy point. So this is a 4, this is a 4. And the buddy point's theorem, as we tend to call it, says the slope of the inverse at 5 has to be the reciprocal of the slope of the original at, and now here, do I want to write a 4 or a 5? Hope you said 4. Okay, these are the two coordinates, 5 and the 4. We have to make sure we're putting the right one in the right part. So then the last task is to find f inverse. We want to use this branch because we have an input value that is 4, and 4 is, you use this part of the definition. We'd find the slope by finding the derivative and then plugging in 4. Your answer should end up being 1 over quantity pi plus 1. So if that's not the case, be sure to ask me in class, but I'll leave that last little bit for you to do as an exercise. You find f prime and then you plug in 4, and there you go. Thank you so much, and I will see you at school.